Okay, so let's start, guys. So today, Bedialauneta is going to be presenting on the realization of a discrete time crystal on 57 qubits on a quantum computer. So let's just take a quick look at the authors of this paper, who are Stephen, Rachel, and Philip Frey, and they work in the University of Melbourne in Australia, and they work in a research group which is called Correlations and Topology in Context Matter, and they basically do research on these three topics, which is quantum computing, strong correlated electrons, and topological states of matter. So it has a lot to do with the paper that is going to be presenting today. And well, you all know Danny, but well, he studies here at the Masters at TU Delft, and one new thing I can tell you about him is that he's going to be doing an internship this summer on C12, which is a company located in Paris, and he's going to be doing some research on characterization of qubits, maybe 2-qubit gates, stuff like that. So that's going to be very nice. And I leave the ground to Danny. He's going to be giving us a very nice talk.
Thank you very much, Alvaro, for the introduction. Well, as you all know, I'm Danny, and today I'm going to be talking about this paper, which was published quite recently. Actually, it was published like on the 2nd or 3rd of March, and it's about that they have realized a discrete time crystal in one of IBM's quantum computers that has 57 qubits. And so the structure that I'm going to follow for this presentation is I'm going to try to give you a feeling for what is a time crystal, but just like in very short, it's like a system that oscillates between two states when you apply a driving force that is periodic in time. And then I'm going to put an opposite idea, which is thermalization, which is that many systems tend towards an equilibrium, while discrete time crystals just keep oscillating and oscillating. Now, the next thing that I'm going to do is, well, present you the experimental setup that they use in the paper and how they do the time crystal, and then I will discuss some of the results of the paper that they get. So, first of all, what is a discrete time crystal? Okay, so a discrete time crystal is a driven system by some periodic force, but the system does not present the same period as the driving force. It presents a longer period, okay? So this is nothing surprising. There are many systems in the world that have this property, and actually Hjalmar, in the previous presentation, he was talking about shining light on some material of some frequency, and then the electron response in the material was of quite a smaller frequency than that one of the light. So what makes a discrete time crystal special? Well, what makes it special, apart from that it breaks discrete time symmetry because of this longer period that it has compared to the driving force, is that there is no thermalization. So what does this mean? You have a driving force that you are applying to your system. It doesn't have that period, but also there is no dissipation of energy, okay? So it keeps oscillating on and on between the same two states, and so it remembers which state was the initial state, okay? And so, before anything, let me try to discuss the first point about discrete time symmetry break, okay? But for this, let me go to space instead of time first, and then we will go to time. So imagine you have a particle. This is your isolated system. Your only thing in your system is this particle. So then, according to the laws of physics, they don't care whether this particle is here in x equals 5 or in x equals 6 or whatever. The laws of physics are the same. And actually, due to Nether's theorem, this leads to the total momentum conservation, right? Instead of a particle, we can also have like a solid, which is constituted of many bodies in the system. But the same thing applies. If you take the whole system, and I don't know, for example, you rotate it, nothing happens. Like the laws of physics stays the same. The system stays the same. The same with translation, but with many particles. If you take the whole system, good. Now, let's look at a breaking of this translation symmetry, for example. So let's go to a crystal. We have a two-dimensional lattice here, which extends all the way to infinity. Imagine that it does. And so here are the ions, and this is the electron. Now, as before, if we take the entire system and we move it, it doesn't make a difference. Like, the interactions are all the same. However, if we look at this electron only, and we maintain the lattice, this electron doesn't have this continuous translational symmetry. No. Because look at here. This electron is interacting with this ion rather strongly. And if you put it a little bit there, far apart, then the interaction is not the same, right? So here we say that the electron breaks continuous translational symmetry of the system, of the laws that govern the system. However, this electron, because it's in a periodic lattice, it does have some other symmetry, which is a discrete translational symmetry. And it's actually the same symmetry that governs this lattice. So for example, if you have this electron here, and which is located quite near this ion, and you move it like all the way to here, okay? So it has the same distance to another ion, but since the lattice extends all the way to infinity, it doesn't really matter with which ion it is interacting, only the relative distances. So here, because the situation is the same, we say that the electron has a discrete translational symmetry. Okay, now let's go to time. So imagine you have a system described by a Hamiltonian, and this Hamiltonian has this term that is time independent, and this interaction term. So let's suppose that this interaction term is periodic in time with period capital D. Then since this doesn't depend on time, then the entire Hamiltonian is also periodic with a period capital T. Now, the thing is that the state of the system, a state of this system that evolves according to this Hamiltonian, does not necessarily present the same period as the Hamiltonian. It can present diverse things, we don't know, but for example, if instead of period t, it presents period 2t, there is a period doubling, and we say that it has broken the discrete time symmetry that governs the Hamiltonian, because this Hamiltonian has some discrete time symmetry because it stays the same every time t. So this state breaks this discrete time symmetry. So this is what happens in discrete time crystals. That the response is not the same as the driving force in terms of periodicity. But as I said, this is nothing special, because let's look at a very, very, very simple example, which is the X gate. So the X gate, you know that X squared is the identity, right? So if you have a system, some initial state, it doesn't matter which, but let's say that it is 0. If you apply the X gate, you obtain 1. And if you apply the X gate again, you obtain 0. So here, there is a periodicity in the driving force of, I don't know, 1 time step. And however, our state has recovered the initial state after 2 time steps, so period doubling. Nothing special about here. Now, what I want to say is one thing, well, 2 things actually. First of all, here we are considering ideal bit flips, ideal X gates, okay? Because what happens if this is an imperfect X gate? What happens is that instead of a pi rotation in the Bloch sphere, maybe you have a pi rotation and a little bit less, okay? So this means that you won't recover the initial state after applying X 2 times. And actually, after you apply X gate many, many times, you will start to accumulate a lot of error. So you will not get an oscillatory behavior, and this means that this period doubling with the X gate is not a stable situation, because many perturbations in the X gate will lead to no oscillatory behavior, okay? And the second thing that I want to say is that a qubit usually is in contact with a thermal bath, okay? Which is at some temperature or whatever. And many times what will happen is that this qubit will thermalize. It will start going into an equilibrium state that is governed by the quantum statistical mechanics with Boltzmann factors given by some temperature T of the thermal bath, etc. But the thing is that once you are in this equilibrium state, you cannot know what was the initial state, because many initial states will tend towards that equilibrium state. Okay? Now, what is the thing about time crystals? Time crystals, well, discrete time crystals, will avoid this thermalization. So discrete time crystals will not go to this equilibrium state, and they will stay oscillating. Okay? Nice. So now let's go to how they do the discrete time crystal. So first of all, they use the IBM Q Manhattan quantum computer. The architecture of the quantum computer is this one. So it's a linear array of qubits, all the way to 56 qubits, which is a lot. And the unitary, the driving force that they repeatedly apply is this one. So they apply it once until time t, then another time, and it keeps going. And it has two parts. First part, already familiar probably, this is the bit flip, the X gate, only that it is imperfect, as I was saying. An imperfect S gate characterized by this parameter epsilon. So it's not a pi rotation, it's a little bit less than a pi rotation. And also note that this parameter is not due to errors of the gates or anything. This is a parameter that the authors set. Like every simulation, they say, okay, now I'm going to go with epsilon equals 0.05. And now the second part of the unitary is this one. So, well, first, this is a 1 qubit case, and we apply each to each of the qubits, right? So this product stands for applying this 1 qubit gate to all of the qubits. And now the second part of the unitary is this one. So again, we have this product over the qubits. So we are applying this 2 qubit gate to each of the qubits. And here, this 2 qubit gate is basically the nearest neighbor Ising interaction, okay? Because you have these sets, and then you have this coupling J between the qubits. Now, this coupling JK is taken at random for each qubit, at random out of this interval here. Now, let me go a little bit more into detail about what these two parameters are, the epsilon and the JK. So, okay, first of all, a discrete time crystal is a non-equilibrium phase of matter, okay? So by non-equilibrium, I mean that you are driving it with a force, and it is oscillating, so it's not in equilibrium. And by phase of matter, I mean the following. So for example, you have this piece of wood, it is solid. And now if you increase a little bit the temperature, it will stay a solid. Unless you increase it all the way up to the melting point where it will melt, okay? Here, something similar happens with a time crystal. So this discrete time crystal will be oscillating. This is like the phase, what characterizes the phase, this oscillation. And it will do so for a range of values of epsilon. So even if you have like imperfect bit flips, for epsilon equals 0, epsilon equals 0.02 or whatever, you have a range where the phase is stable and maintained, okay? And the second thing is these couplings, JK. I'm not going to go very much into depth in these things, but it is necessary for the discrete time crystal to appear for these couplings to be taken at random, so that there is disorder between the interactions of the qubits, okay? This is because this is necessary for many body localization to appear, which is a condition necessary to avoid thermalization. So basically, a discrete time crystal is a specific case of many body localization. But this is just a necessary condition. I will keep it like that. So, before looking at the results of the paper, let me just try to predict some things. So, what happens when epsilon equals to 0? And we have 2 qubits. So, imagine we start in the initial state, 0, 1. Well, first, let's apply the perfect bit flip, because now epsilon is equal to 0. Well, a perfect bit flip will simply go from 0, 1 to 1, 0. No problem. And then if you apply this second unitary, since you only have set gates here, or set Pauli set matrices, and this is an eigenstate of the Pauli set matrices, nothing will happen. You will get a prefactor here, but okay, you still have 1, 0. And now let's apply this unitary a second time. So you apply again the perfect bit flip, so from 1, 0 you go to 0, 1, and you apply the second unitary, and you get an additional prefactor. Okay, so this simply means we have gone from 0, 1 to 1, 0, and from 1, 0 to 0, 1. So we are moving all the time between basis states. But this is only for epsilon equals to 0. For epsilon not equal to 0, what happens? Well, imagine this is an imperfect X gate. So when this imperfect X gate acts on this 0, it will not give 1, it will give a superposition of 0 and 1. And the same when this imperfect gate acts on this 1, it will lead to a superposition of 0 and 1. And now you will have like a superposition of 0, 0, 0, 1, 1, 0, 1, 1. And when you apply this second gate, each one of those terms will receive a different prefactor, okay? And this will lead to entanglement of the whole system. Okay, we are prepared now to look at the results. So these are the results. What do we want to look at? What are we looking for? We are looking for oscillations of the total state of the system, okay? So, how do we do this? First of all, we initialize our system in some state. We do this by simply choosing a random bit string for each qubit. Well, no, a random bit string that will be our initial state. So, for example, 0, 0, 0, 1, 1, 0, 1, 1, 0. Okay. And then what we do is measure the value of the Pauli set matrix of each qubit at all times. Okay. We don't really care about the specific value of the set Pauli matrix. We care more how it relates to the initial value of the set observable. So what we care is whether it is oscillating with respect to the initial state. So here, this term is like a correlation in time of the observable set in each qubit. But remember, we don't want to look at oscillations of each individual qubit. We want to look at oscillations of the total state of the 57 qubits. So what we do is take an average. Take an average of the correlation times of all the qubits, and we obtain like an average correlation time of the total system and stuff. And this is what they get experimentally. So here you can see some oscillations. To go from this point to this point, you are applying the unitary gate once, and from this point to this point, you are applying it once again. So here, the period of the driving force is this one, but you recover the initial state when you apply it twice, so we have period doubling, no problem, this is good. But this is not the graph that we are looking for, because here the oscillations are getting damped. And so what they do, there is a reason for this, they apply an error mitigation scheme. So as I told you before, in the case of epsilon equals to 0, we said that we always move between basis states, right? So this means that throughout all time, these states that the system is in will be an eigenstate of the Pauli set operator. However, what they see experimentally is that for epsilon equal to 0, there is still some decay. So in principle, if there was no decay or no errors, you would see here oscillations plus or minus 1 for the case epsilon equal to 0. But since there are errors, you see a decay. And what they do is they take this decay for epsilon equal to 0 as a reference to correct the decay of the epsilon not equal to 0 cases. Okay? And when they apply the correction, they obtain this graph here, which is way nicer. And so what do we see here? We have these green dots and the blue dots, and they are both for an epsilon of 0.05. And also, the green one is for an initial state which is completely polarized, so 1, 1, 1, 1, 1, 1. And the blue one is for a random bit string, so what I said, like 0, 0, 1, 0. And so what is interesting is that no matter what initial state you have chosen, you get oscillations. These like super stable oscillations throughout time, you get them. Also, I will show you later, but no matter what epsilon value you choose inside an interval, you will also get stable oscillations throughout time. And also, no matter what couplings you choose here, as long as they are random and in this interval, you will also get oscillations here. So it's like somehow these qubits, you're applying some driving force, and they are this noise generated by the couplings stabilizes the state to have it all the time oscillating. Okay? And this is what makes it a phase of matter. This robustness against the parameter epsilon and so on. So here they also do well a Fourier transform of this signal in time, and clearly, as I already told you, they get a peak in half the frequency of the driving force. And now let's look at this, what I was saying, this interval of epsilon where the phase is stable. So let's go with this graph, which is easier. In this graph, what are we plotting? We are plotting this delta here. What is this delta? Okay, so you take a qubit, and in principle, well, you look at its set observable. But you look at the absolute value. So in this case, when you look at the absolute value of the set observable, you would have all these points going up, and so you would have a nice curve here, right? So now what you do is this curve, you feed it with an exponential, okay, to see how it decays the state of the qubit, or basically to characterize the depolarizing noise. So what they see here is that for these values of epsilon, the signal does not decay exponentially or anything. And here in this, at this point afterwards, there is a transition, and you get, here you already are in the thermal regime, and you start to have, well, basically the discrete time crystal disappears, and you have decay of the qubit. So basically, we are seeing here how the discrete time crystal avoids thermalization. And yeah, okay, so these were the results. Now, a little bit conclusions, what I want to leave you with after this presentation. Basically, what are discrete time crystals? So they are a non-equilibrium phase of matter, non-equilibrium because they are oscillating states and you are driving it with a force. And also it's a phase because of what I said, that it's a solid, it's not a solid, but I mean, it's robust against external parameters. It maintains what characterizes the phase. Then also, they are possible thanks to many-body localization. I haven't gone into what is that, but if you are interested in these kinds of topics, many-body localization will be like the main concept and what is behind all of this. And then, as a consequence of many-body localization, discrete time crystals avoid thermalization, they keep oscillating, and they remember the initial states. So, they are kind of cool because people are saying, well, maybe we could use discrete time crystals to make quantum memories or so on because they maintain the initial state. But yeah, this is like a very futuristic application maybe. And, yeah. So this was it. Thank you very much.